Okay, hi. I'm Taus, and I'm a postdoc as well on the VMS thematic project. And I'll talk today about, well, first of all, the compilation there that you've seen some people use that we finished, I guess, a year or two ago. That is readily available on the Merck website. So if people want to use them, they can download them and do with them what they like. I'm focusing on felsic volcanic rocks, as you can see from the title. So it's really how we've used these two compilations to capture, I guess, a geological attribute or feature, which is the felsic volcanic rocks, and then see if that can sort of inform us on VMS endowments. So I'll just start with a slide here that is sort of preaching to the choir. But yeah, the general overarching thing that we want to solve with Metal Earth is really this question about differential metal endowments. And the maps that you see here is going from a world map with all the Archean cratons in sort of the dark gray here, and then the pie charts showing the VMS distribution, and you can see like the Superior here with the biggest pie has around 120 VMS deposits compared to some of these other Archean terrains, for example, the Pillbearer down here, and the Yilgarn with each around 10, so like an order of magnitude difference. And that would also come through if you took into consideration the surface area of these, that the Superior is way more endowed. So this differential endowment in VMS is something that we see as we move beyond sort of the larger scale and go down to here, the Abitibi. Again, the VMS deposits distributed sort of heterogeneously throughout the greenstone. And again, you can move into a closer area here in the Noranda camp, where we have the deposits again sort of clustering in different areas on the district scale. So this work is sort of really just trying to put a dent in our understanding of why this clustering occur. As I said, we're focusing on the sort of the felsic rocks, and of course, it wasn't lost on previous workers that the felsic rocks had some significance in the VMS formation. This is an excerpt from Franklin's SEG paper here, just noting how these felsic intrusions have been interpreted as a product of high heat flow and crustal melting. So that's well known, and associated volcanic intrusions have been thought to be the drivers of the hydrothermal systems producing the VMS. And of course, the geochemistry of these have resulted in the F classification, sort of developed by Mike and Harold, and this is often used also to give sort of an indication of depth of the source of these melts. And if you have the right systematics, it would indicate that you have shallow melts in your crust, and those could potentially indicate higher heat flow that can drive the hydrothermal systems. We're going to look at sort of the distribution of felsic rocks, and that also is something that people have addressed in the past. This is the map you just saw from in Keaton's talk. So again, these are these volcanic complexes that Goodwin and Riddler mapped out some decades ago. I just want to highlight within these complexes, you can see the cross-hatched areas here is them mapping out the felsic volcanic rocks, showing that there is a spatial association here with the felsic volcanic rocks and these volcanic centers. And of course, if you put the VMS deposits on there, they also seem to fall within these complexes, and thus making that spatial association with the felsic rock something that has been recognized. However, what we really want to try to do is to sort of do a more quantitative approach so that we can sort of really convince ourselves that the crust is different in these areas where we have this felsic rocks, and tie that to the VMS association. Now, I was first involved with the transect projects, and I was working in the Noranda camp, and we tried this method there to sort of show how the features that we saw in the geophysical sections, how that related to the geology at surface. So one of the things that we did in the Noranda camp was to try and do a surface proportion estimate of different rock types. So the white stipple lines here are essentially the different synvolcanic faults and the fault blocks that they form, that the map has been divided into. And then within each of these fields or areas, we did a surface calculation of the different lithologies within them. And in this case, the color scheme is pretty standard for what we're used to. Felsic rocks in yellow, mafic rocks in green, some mafic intrusions and synvolcanic intrusions in pink here. And what we end up with is that where we have the highest proportion of synvolcanic intrusion, TGGs, and felsic volcanics, it's also where we have the greatest metal endowment. And it's also where we get the highest fault intensity, or the most faults across the transect. So applying that to the entire Abitibi was initially a bit of a problem because, as you all know, the provincial boundary cuts right down the middle, and getting one side to agree with the other side has been a problem over the years. Fortunately, I didn't have to care too much about those politics, so I just took the maps from the geological surveys and tried to put them together as best as I could, which meant that you ended up with a map relying on the OGS legends, because their legend entry counted 19, whereas I think Quebec was well over 100. But nonetheless, that sort of that allowed us to create a lithological map that's like uniform across the entire Abitibi, relatively simple in terms of lithologies, but at the very least we could capture sort of the felsic volcanic rocks. That was then all the line work in those maps are directly tied to the assemblage map that we then created as well, so that we could start doing calculations of these different features within each assemblage, so within each sort of time interval, as Keaton pointed out earlier. And that allows us to do some of these calculations right off the bat, just looking at the size of each of the assemblages. So here you have the pie chart corresponding to the x-axis down here in the color scheme of the different volcanic assemblages, and we are going from sort of the older assemblages to the younger, and the curves here illustrate cumulatively growth, or sort of area, I guess. And you have also cumulative gold endowment in VMS related gold, and also cumulative copper plus zinc in million tons in the blue here. So you can see that it shows you how the volcanic package grew over time, with some small contributions here to start over many years. So how accurate that is might be difficult to say. But then you get into the Deloro and the Stockton Rockmauer, where we really start building with the Deloro here corresponding to almost a quarter of the pie up here. The Stockton Rockmauer, the biggest assemblage, but you can see that occurred over a very short time period. So it sort of gives a first order feeling for some differences in these different assemblages in terms of the amount of time it took to build the whole volcanic stratigraphy. That also allows us to calculate these nominal growth rates and nominal, what do I put down here? Oh my God, can anybody read that? It should be spreading rate, yeah. And those calculations, they're very similar to what Mark and his group has done in their recent paper on applying sort of the microplate model to the Achaean. But again, you can see from those that the Stockton rock mower here really stands out as something that was produced really fast and took up a lot of space. And at the same time, if we look at the metal endowment, we can see that that's a period where almost nothing happened in terms of the VMS space, whereas some of these other assemblages like the Deloro and the Blake River really had some big increments in VMS. Another way of looking at that is simply the contained metal and also the endowment, where we take into consideration the surface area. And again, that sort of shows this differential metal endowment also between the assemblages with the Deloro and the Kit Monroe and the Blake River as some of the most productive of VMS endowed. We can also go and look at the volcanic rocks. So here are the pie charts for the different for the Abitibi overall, and that's like a value I will get back to here. That is the 7%. So that's what I will refer to as like background. So that's background felsic volcanic rocks in the entire Abitibi, if you are looking at just the greenstones. And then you can split that up by assemblage, and that also sort of paints a pattern, or at least some trends where you see the more endowed assemblages like the Deloro and the Blake River at like 9 and 10% felsic rocks, compared to the less endowed Stockton rock mower that is like less than half of the proportion of felsic rocks. So to sort of put that in the VMS space, what we really wanted to do was to try and see if the VMS areas are truly sort of has this spatial association to the felsic rocks. So what we did is we used a database that Krusniski, together with Pat and Ross, put together, and Pierre-Simon Ross, which has 101 VMS deposits or occurrences, like with some geological resource. And then I essentially drew a circle around the big deposit in an area and included all other deposits within that area. Those circles are 15 kilometers in radius, which sort of matches Sangster's idea of the average size of Canadian VMS districts across Canada. And then if a deposit fell outside, or whatever deposits fall outside like one of these centers, will then be incorporated into another center until all the 101 VMS deposits are accounted for or belongs to some VMS center. So that ends up with a total of 34 districts or centers, as we ended up calling them. And then within those centers, we calculate the proportion of felsic rocks. First, though, we will constrain, and that's one of the things that Keaton pointed out, that they didn't have the geochronology back then, but we are, of course, using the assemblages, so we're constraining these centers by assemblage before we calculate the proportion of felsic rocks. And what we find is that about 70% of these VMS districts has a higher proportion of felsic volcanic rocks than this background 7%. So then the next question became, is that really, should we consider that special? So that's when this whole Monte Carlo part comes into play, where we essentially ran these simulations. So we ran 1,000 simulations where we matched the number of VMS centers that we established, which was 34. And then we just had random spots generated across the Abitibi, calculated the proportion of felsic rocks within those, and then saw if it exceeded what we saw in the real data. So as I said, we ran 1,000 of those, and the process is sort of given on the left side here, where we have a point, then created like this buffer zone, then the buffer zone was cut, so it matched the assemblage in the area. And then here you can see the orange is the felsic rocks, so then we calculate the proportion. So we did that 34 times 1,000 times, and the result from those simulations, well, not a single one could produce the observed results. So we took that as that this association that we see in the real world is not by chance. We also sort of did an extended Monte Carlo, I guess we ended up calling it, where we also looked at all these 35 or 34,000 fictitious or simulated areas, or VMS areas, and saw if there was VMS within these random areas, and then when there was VMS in them, did they exceed the background levels of felsic material. And that's just one example of that. So here's the random spot. It just happens to have one VMS deposit, and then the calculation in this case here is 12% felsic rocks, so above that background. But when we look at that data, we can see the two bins there that you see is one bin where you see no VMS, the two bins shows where you see VMS, but the left one is where you see VMS in lower than like background felsics, and the one on the right side is where you see more than this background, and you can see that it's almost a five-fold increase in VMS success when you have more than background felsic rocks. And you could also split that up by assemblage, and it sort of is very similar for almost every assemblage, and a very strong increase across those endowed assemblages, especially like the Deloro and the Blake River. So that gets me to the point where we can start sort of thinking a little bit, like we have now allowed ourselves maybe to think a little bit about what's going on, and the fact that these areas have more felsic rocks than background seems to suggest that they have sort of exceeded, or like they are different, and we think of it as they have exceeding this transient heating and developed the crustal conditions capable of allowing these shallow crustal reservoirs of melt that also allowed for the felsic magmatism. And when you look at some of the modeling that exists in the literature, we can refer to that as sort of thermal maturation. And that's not something that necessarily happens overnight. That does require that you are pumping the crust full of first a bunch of mafic rocks, allowing the temperature to rise to the point where you can start melting your crust, and then also allowing mushes or whatever you want to call it, intrusions at higher levels to exist for prolonged periods of time without stalling or freezing, so that they can drive these VMS hydrothermal cells. So just on the modeling here, you can see that they have like two stages where first they're pumping the lower crust full of mafic magma, and that then at some point later it allows these magmas also to reach higher and sit up here, potentially driving hydrothermal systems. And the thermal maturity is to be thought of as when this range of change in the temperature essentially becomes zero or like close to zero. So in this case here, which is not, maybe the tectonic setting that we are looking at, but in this case here, you can see that getting to those conditions where your crust is thermally mature that can allow this takes millions of years. And then the Middle Ocean guys likes to go from the Middle Ocean to the Abitibi, and I like going the other way. So I'm also piggybacking a little bit on, on all that great research they've done. So one tectonic configuration that may promote this sort of thermal maturation, in my mind, would be something like the northern Lao Basin, where you have sort of this distributed rifting. So where, you have a lot of rift segments, but where the spreading rate might not be as high as you would expect sort of down here in this area, where it's like a single rift with much higher spreading rate. So that might be more sort of a Stockton Rockmauer setting in my mind, whereas this up here might be sort of a Deloro Blake River situation, where you have this distributed rifting over like a wide area. And one of the things that we can do is, Keaton showed that nicely as well in his slide, like a blow up of one of these triple junctions they have in the North Lao Basin. So here, just like him, trying to compare these at the same scale. So here I put up the Noranda camp with the two transcrustal structures, and you also have the Ron Penna here. So thinking of these as magmatic centers that are building along these rifts would be one possible way to create these condition that will allow this increased amount of felsic rocks. So having two felsic centers building right around these transcrustal structures seem to be a good scenario. So yeah, I'll wrap it up. That's the conclusion slide. So yeah, I don't have to read through that, but that's it.